In this video, I'm going to discuss some reactions that ethers will undergo. Now, ethers generally are unreactive in basic or mildly acidic conditions. So, ethers generally unreactive in either basic or mildly acidic conditions. So, however, in strongly acidic conditions, acidic cleavage can occur. And in acidic cleavage, an ether is converted into two alkyl halides. So I'll show that mechanism right here. So in step 1, we've got diethyl ether here. I'm going to use a strong acid like HBr to protonate the oxygen. Now I have a good nucleophile in bromide that will come in and I'll be left with now ethanol and bromoethane. In step 2, the ethanol is going to get protonated by HBr again. And now it's just standard SN2. You see this all the time. A good leaving group, a great nucleophile will come in, and I'll get water and bromoethane again. So this is acidic cleavage. You start with an ether, the first reaction, you'll end up with an alcohol and an alkyl halide. And then that alcohol will react with strong acid to give you water and another alkyl halide. Now, one thing to note here, this is best with HI and HBr. It's okay with HCl. It doesn't work as well with HCl, and it does not work with HF. So just something to note with this reaction. The second thing that ethers can do is undergo auto-oxidation. And this is something that can happen in any conditions. If you have a bottle of ethers that you've been storing for a very long time in the lab, there's the potential that it could have undergone auto-oxidation. And you have to be careful because the product of the auto-oxidation is very reactive. So this is going to be a free radical reaction. So in step 1, our initiation, I've got my ether. In this case, it's going to be ethyl-methyl ether. Ethyl-methyl ether here. This is going to react with an initiator. So all this is some sort of free radical. It'll undergo a hydrogen abstraction. And I'll get now my free radical plus, we just lose the hydrogen to whatever the initiator is. So because we don't know the exact initiator, I won't write that in. So next is going to be the propagation. So in the propagation, my ether radical will react with atomic oxygen. Or molecular oxygen here, because we have O2. So I haven't lost my radical. My radical is here now, right? Because you don't lose any radicals until you get to the termination. So next up, this will react with another one of the initial reactants that we had. But now, basically, you can think of this has become the initiator. Right, it's become the initiator. So I end up with my product here plus the ether radical again. So this is the product. This is the dangerous compound formed from autooxidation. And of course, because I'm still in the propagation phase, I regenerate my ether radical, and it'll keep undergoing these reactions. Then in termination, 2 of the ether radicals will react with each other. And I'll draw them this way to make it easier to draw the final product. Right, the 2 radicals combine, and I'll get my final product. So this is auto-oxidation of ethers, and this is going to happen to any ether if it's exposed to oxygen for a long period of time. Right, so you especially don't want to leave your bottle of ethers just open in a lab. Even when you close it, it'll get some oxygen in there. It'll undergo this auto-oxidation over time. So just make sure with ethers in your lab to be careful with them.